Howdy and welcome back to Wheeler Scientific. In today's video, I'll be combining both the scientific glassblowing series along with my element series to show how to bottle liquid chlorine gas in a high pressure ampule. Normally chlorine exists as a gas at standard pressures and temperatures, but if we cool it down, we can liquefy it. If we also increase the pressure around it, we can liquefy it. Therefore, if we take it, liquefy it, put it into an ampule, and seal that ampule, when we bring it up to room temperature, the pressure increases, which then keeps it as a liquid. And due to its relative low psi, around 70 psi, we can do this in a glass vessel. And then we get a beautiful sample of chlorine gas that is now a liquid at room temperature. To begin, we need to find either a well-ventilated area or go outside. In this choice, I decided to go outside. Once outside, we need to generate the chlorine that we're going to put into our ampule, and this can be done through chemical processes. There's a few ways you can go about this. One is electrolysis of a chloride-containing salt, such as sodium chloride or manganese chloride, but this requires a specialized cell and is a bit more complicated. There's more straightforward ways of going about it. One of them is to react with hydrochloric acid and pyrrolysite, also known as manganese dioxide. This produces chlorine gas. Another way to produce chlorine gas is also reacting hydrochloric acid with stabilized chlorinated powder for pools. And I have a lot of stabilized chlorine around, so I'll be using that method. This is a basic setup that I used for it. On the top, we insert our hydrochloric acid, and then this drips down into our reaction flask, and we have a barbed connector which then outputs the gas. This is a very simple setup and can be made in a few different ways. One of them is using a separatory funnel into a vacuum flask with a cork connected to it, and the vacuum flask already has a barb that you can output the gas with that, and it's a simple method to go about doing this process, but if you have the equipment, I recommend the ground glass fittings as you have a less likely chance to leak once you properly grease them. In this case, I greased them with some sulfuric acid. Once the gas is produced, we need to dry it, and in this case, I'm using some calcium chloride. Because calcium chloride is already a chloride, it won't react with the chlorine gas and only pull out the water, leaving us with our dry chlorine. And this chlorine is then piped to our ampuling stage. At the ampuling stage, we have a pasture pipette which then leads into our ampule, and our ampule is in liquid nitrogen. It's important to not use a pressurized system. If you connect the tube directly to the ampule, you won't get any liquefaction of chlorine, because the chlorine won't displace the air as effectively and won't get pushed into the ampule. By using a pasture pipette, this ensures that the chlorine makes it into the vessel, and it also doesn't overpressurize the system. You want to be careful with your positioning of the pasture pipette too. If you position it all the way down into the liquid nitrogen, then it might freeze over and cause a clog. So what I like to do is position it above the level of chlorine, outside the reach of it, so it sprays the chlorine gas into it. And because chlorine gas is denser than air, it'll displace the air and fall into the vessel, allowing it to be liquefied and collect over time. A pasture pipette can be easily manufactured from some basic 10mm tubing. You're going to want to heat the center and then pull it out, just like you're pulling a spindle. Then cut it in half and you're left with your pasture pipette. Now when it comes to cooling the chlorine to be liquefied, there's a few methods you can go with. You can either use a mixture of dry ice and acetone, or you can use liquid nitrogen. For most, it's going to be easier to use a mixture of dry ice and acetone, but this also has some downsides. It's a lot warmer in comparison to the liquid nitrogen. Liquid nitrogen won't only liquefy, but freeze the chlorine. This makes it a lot easier to work with. I have tried both methods in the past, and I find that using liquid nitrogen is vastly superior than using the mixture of acetone and dry ice. You can cool stuff down a lot faster, and it's a lot easier to work with. Now that we have our setup all ready to go, we can add in the liquid nitrogen and get the chlorine generating. We can add in hydrochloric acid to the top addition funnel. We can then open up the stopcock and begin dripping that HCl onto our stabilized chlorine. This will generate the chlorine gas, which then will soon displace the air and lead into the ampule, where the liquefaction will soon take place. Once the ampules are filled, you can move on to the sealing stage. Now, I don't recommend making liquid chlorine ampules as it's quite dangerous because you're both working with extremely low temperatures, extremely high pressures, high temperatures, and you're also working with an extremely caustic liquid. Sealing these ampules can be quite difficult. First, you're going to have to let them warm up a bit. This is because there's some carbon dioxide which has solidified inside the ampule also. This needs to be driven off first so that we can easily seal it. This carbon dioxide is going to be a big issue if we don't get rid of it. Upon melting all the liquid chlorine also, it goes to the bottom of the ampule. This makes it much easier to work with also. Next, we're going to refreeze all of the liquid chlorine back to a solid. Once that has happened, we then take it out and remelt the chlorine. But in this case, we're not going to completely remelt the chlorine. We just want there to be a presence of chlorine there to fill up the vessel. Next, we're going to do a quick pull seal up towards the top of the ampule. This seals off the ampule and creates the vessel. We then cool it back down in the liquid nitrogen. Now what's happening here is we're treating the high pressure ampule as if it was a low pressure ampule. Because we let the chlorine go back to a state of liquid, some of the chlorine evaporated and took up space in the container, displacing any air that would be present. We can then put it back in the liquid nitrogen, cause the liquid chlorine that was now a gas back into a solid, creating a negative pressure. This negative pressure allows the ampule to be sealed so much easier and produce a better seal overall. Once it's solidified, we can go back to melting it. Now, when it comes to sealing these ampules, you have to be slow and steady. Treat it like a low pressure ampule. If you heat it too quickly, it'll quickly suck in all the glass and pull it in, creating a quick seal. Now, you want this to slowly pull in, and you want to heat one side evenly, and then dip it back into the liquid nitrogen, pull it back out, heat the other side, dip it back into the liquid nitrogen, and continue heating until it contracts in, and you get a nice seal. Then you can do the cosmetic work into forming a nice point on the ampule. Once the nice point on the ampule is finished, we can throw it back into the liquid nitrogen. Once we have it cooled down and frozen again, we need to put this somewhere where it can warm up. I'll be throwing it into a cardboard box full of sand. This will give it time to warm up and keep it safe in case it detonates. You may notice as soon as I started working with high temperatures, I took off the nitrile gloves. Now, I didn't put any other gloves on because I still need to have a tactile sense of being able to move the glass back and forth. Also, you should never work with high temperatures and nitrile gloves, as if you touch anything hot with the nitrile gloves, they will stick to your skin and melt to it and give you severe burns. Now, if you want, you can use some gloves while melting the test tubes shut, but I don't recommend that as it can give you a false sense of security and you might catch your gloves on fire. I find that due to glass's less thermal conductivity as it's an insulator, there's a region between the really cold and really hot where you can touch where you're not going to have any problems. Glass is an insulator, so you can touch quite closely to something that is either a low temperature or high temperature and not have any issues. I usually leave like this middle region where it's warm enough that I can touch it without having any issues. Once the ampoules have warmed up to room temperature, we then need to thermally test them and make sure that they are able to withstand pressures. Right now, they're holding around 70 psi, but it's good to test them above that because right now they could still randomly decide to detonate. We can do this by putting them into some hot water. I like to use boiling water, so I thermally test them to a point that they should never ever reach again. For thermal testing, I throw them into a metal tube and then put this metal tube into another metal container. I have this metal container resting on some bricks and I put some bricks on top of it. This will contain them in case there's any detonation of the glass vials and keep the glass from going anywhere. It also will stop any cascading effects happening. If one was to detonate right next to one, it might shut off the next one. So by putting them in metal tubes, I keep that problem from happening. After the water is poured in, some time is let pass until the container cools back down to the ambient temperature. At this point, the ampoules can be removed and examined. As long as they didn't explode, they should be good to go. I went ahead and made a bunch of ampoules, so I thermally tested those too, and here they are all done and complete. Now, I wouldn't completely trust these, because they still are glass pressure vessels, so what I like to do next is then seal them into some acrylic epoxy. This will then keep them safe, keep them from shock resistance, and contain if they do explode. It also makes them a lot stronger during transport, and it's a better display case item. Once you're all done, you're left with a beautiful ampoule in some acrylic epoxy. Thanks for watching, and I hope to see you again. If you have any comments or questions, post those in the comments section below. If you liked the video, drop a like, and if you like my content, consider subscribing. I hope to see you again. For now, see you later.
Well, I don't know, but I've been told uranium ore's worth more than gold. Sold my cad, I bought me a Jeep. I got that bug and I can't sleep. Uranium fever has gone and got me down. Uranium fever is spreading.